For inviting me to give a talk here. So my talk is about picking and covering something in graphs. So what are the topics? So several problems in combinatorial optimization or in graph theory can be modeled into these two types of problems. So the first kind is called the picking problem. The other is called the covering problem. So first we fix a set of graphs, say F. Then given a graph G, I want to find the maximum number of disjoint subgraphs, each isomorphic to a member of F. And for the covering problem, I want to find the minimum number of vertices that are required to touch all such subgraphs. So if you know combinatorial optimization, these two problems are dual of each other. But let me just show you some very easy example. So for example, if F just contains one graph, K2, so just an edge, then what's the maximum number of vertex disjoint edge I can find? It's the maximum size of a matrix. So the optimal solution for the picking number is just the maximum size of a matrix. And how about the covering problem? So I want to find the minimum number of vertices that touch all edges. So in other words, if I delete those vertices, then I have no edges remaining. So exactly the vertex cover. So the optimal solution of this case is the minimum size of vertex cover. And actually, in general, there are some relation between the optimal solution for the picking problem and covering problem. So if I call the optimal solution for picking problem P, and the optimal solution for covering problem is C, then P is at most C. Because if I have P vertex disjoint subgraphs, then I need P vertices to touch all of them. So P is at most C, no matter what F is. But sometimes I can bound C in terms of function of P. And for example, if in this easy example, if F just contains K2, then we can show that the minimum size of vertex cover is at most twice times the maximum size of matrix. Because if you pick a maximum size of matrix, then you pick ends of the edges in the matrix, then they touch everything. Otherwise, you can increase the size of the matrix. So that's exactly what the Eldridge-Pochard property means. Like, it describes when I can bound the solution of the covering problem in terms of function of the picking problem. So let me make it formal. So we say a family of graphs has an Eldridge-Pochard property if for every number k, I can find another number depending on k, such that any graph G either contains k disjoint subgraphs, each isomorphic to a member of F, or I can find n vertices touching all such subgraphs. And this property gets this name probably is due to a classical result of Eldridge and Pochard. They prove that the set of cycles has the Eldridge-Pochard property. So in other words, every graph either contains k disjoint cycles, or you can kill all cycles by deleting at most nk vertices. And small families are known to have the Eldridge-Pochard property. So one example is Thomason's theorem. He proved that if the family of, so fix a number n, then the set of graphs of length 0 modulo n has the Eldridge-Pochard property. However, it's also known that some families doesn't have Eldridge-Pochard property. So here is an example by Discrete and Numenara. He proved that in the Thomason theorem, you really need 0 modulo n, because he proved that if consider a set of cycles of length non-zero modulo n, then Liu has no Eldridge-Pochard property.
Is this old here?
It's pretty old, yeah, probably 80s. Okay, so let's go back to Eldridge-Pochard's result. This result was generated by Robertson and Seymour in terms of graph minors. So we say a graph G contains another graph H as a minor if H can be obtained from a subgraph of G by contracting edges. Now I write the set of graphs containing H as a minor as M of H. And Robertson and Seymour proved that M of H has the Eldridge-Pochard property if only if H is planar. So it gives another characterization for planar graph. And it also generalizes Eldridge and Pochard's result because the set of cycle is the case when H is just a loop. Okay, so but in this talk, we'll consider some other graph containment relation similar to the minor relation. So one case is the topological minor. So we say a graph G contains H as a topological minor if H can be obtained from a subgraph of G by suppressing 30 of degree 2. So it's closely related with minor relation because one example is the Kuratowski theorem. Your graph is planar, then you have no K5, K33 as a minor, and if it has no K5, K3 as a topological minor. Okay, so if I write the set of graphs containing H as a topological minor as T of H, now I want to prove something like Robertson-Seymour's theorem. I want to find a characterization for the graph H such that T of H has the irreducible property. And it's actually a one question asked by Robertson-Seymour in the same paper they proved this theorem. So in this talk, I'll show you such a characterization. So first, let's see some necessary conditions. So the first one is proved by Thomason. Now, if T of H has the irreducible property, then H is not only have to be planar, but you should be able to draw H into the plane such that all vertices of degree at least 4 incident with the infinite phase. So it's a topological property. But this topological property is not sufficient. And here's an example. So let's consider this tree H. So tree is autoplanar, so we can draw into the plane such that all vertices incident with the infinite phase. But I'll show that T of this tree has no irreducible property. So you pick a large wall, arbitrarily large, and then you delete the top vertex of the tree. You get 3 disjoint subtree, and you make a copy of them, and then attach these copies to the bottom row of the grid of the wall, such that the copy of the first tree are at the left, and the copy of second tree is at the middle, and the copy of third tree is at the right. And then you can check G contains one H subdivision, one H topological minor. But I'll show you that you cannot contain two disjoint H topological minors, because all the H topological minor should look like this. It's exactly what the picture shows you. So why? So if I have a H topological minor, then let's see the branch vertex of this degree 6 vertex. The branch vertex of degree 6 vertex should have degree at least 6. But only degree 6 vertex in G are in the copies of the first tree. So the branch vertex in the first tree should be also in the copy of the first tree. And secondly, you see this degree 5 vertex. So the branch vertex of this degree 5 vertex should have degree at least 5. But there are only 2 kinds of vertex in G have degree at least 5. One is contained in the copy of the first tree or in the copy of the second tree. But this vertex has 2 neighbors of degree at least 2. But this vertex has no 2 neighbors of vertex degree at least 2. So the branch vertex of this one should be in the copy of the second tree. And similarly, you can check the branch vertex of the third subtree should be in a copy of the third subtree. And then you need some path to connecting those subtrees. Then you can see you cannot find 2 disjoint H topological minors in G. So it shows that T of this tree H has no irreducible property. Okay, so what this example tells us? The key point is that if I delete the top vertex, I get 3 disjoint subtrees, and these trees are pairwisely incomparable by the topological minor relation. So that's why I can construct an example. So let me make it formal. So now I fix the graph H. And if I have a subgraph S of H, I want to define the rooted subgraph S plus in this way. So don't read this, it's complicated. So it just means I have a graph H here, and I have a subgraph S here, and there are some edges between S and nothing S. Something like this. I probably can have the parallel edges. Okay, and what is S plus? S plus just, you see the picture here. So S plus will be this S is S plus. You have 3 edges like this, so it becomes this. So wherever you have an edge between S and the non-S, then you put a leaf attaching where it should be. If it's the parallel edges, then it becomes 2 leaves, something like that. Okay, and then these new vertices are called the roots of S plus. So now I have rooted graph. So now I want to compare 2 rooted graph. I say S plus is less equal to T plus if T plus contains S plus as a topological minor, and the branch vertices of the roots of S plus should be also roots of T plus. So roots should map to roots. So now I can define a notion that's called a cover. So a cover of a graph H is a set of disjoint subgraphs of H such that the following holds. So the first condition is that every vertex of degree at least 4 in H should be containing one member of the cover. So that's why it's called a cover. And the second condition says all the members are required, means that every member should contain at least 1 degree 4 vertices in H. And the third condition is a minimality condition. It says that no member can be further refined. So it means that if I pick any member S in C, then I cannot find disjoint subgraph T1, T2, and so on of S, such that the union of those Ti contains all vertices of degree at least 4 in S. And each Ti, and for each Ti, I can find another member of the cover such that Ti plus is less equal to Si plus. Then it means I should not put S into the cover, right? I should put T1 through T1, T2, and so on into the cover instead of putting S into the cover. So this condition just means every member of the cover is somehow minimal. Okay, so that's the definition of a cover. Then by using the similar idea to construct a counterexample as the case for the tree, we can prove another necessary condition. So if T of H has error disclosure property, then H cannot have a cover that contains 3 pairwise incomparable maximal elements in the cover. Now I compare the graphs according to the rooted topological minor relation just mentioned before. Okay, but now I have 2 necessary conditions, but these 2 necessary conditions are still not sufficient. So let's consider this graph H. It's an alterplanar graph. So again, I can draw every vertex. I can draw this graph into the plane such that all vertices incident with the infinite phase. And I only have 2 vertices of degree 4. So every cover has at most 2 members, because every member should contain a vertex of degree at least 4. So I cannot have 3 members in the cover. So this graph satisfies all properties I mentioned before. But now I show that I still can construct a graph such that I can only find 1 H topological minus, and I cannot delete all H topological minus by deleting bounding number vertices. So here's a graph that I construct. So pick a large wall. And now I only draw 4 rows in this wall, but I want many rows. I just don't have enough space. So it's a very large wall. And then I identify the first column and the last column in the same direction. So I get a cylinder wall. And then I cut H in the middle. And I get 2 isomorphic subgraphs. Then I attach I make copies of these subgraphs and attach them into the bottom row and the top row in the picture I show you that. Then I can find the H topological minor like this. But again, we can show that all the H topological minors should look like this. They should really go around the cylinder. So we cannot find 2 disjoint H topological minors. Okay, so what's wrong in this example? What does it tell us? The problem is that if I cut edge in the middle, I get two subgraphs. So they form a cover of the graph edge. And if I give an ordering of the roots, so if I cut in the middle, the roots are given by these two edges. So each member has two roots. So I can give an ordering of the roots. Say the top edge gives the first root, and the bottom edge gives the second root for the left-hand side member. Then, if I want to give the same ordering of the right-hand side member, I mean, fix the ordering of the roots, then this one is containing the left member in the topological minor relation. But if I want to make the roots matched, then I should say this root is the first root and this root is the second root. Now, if I want to go along the boundary cycle by saying I want to see the first root of the left member and the second root of the second member, and then the first root of the right member and the second root of the right member, then I have to flip it over the right-hand side member. Then I'll get a cross in the middle. So let's make it general. So I mean, what's wrong in the previous example is that the members are not symmetric with respect to their roots. So I want to define some symmetric condition. Okay, so first I have a rooted graph S plus. Now I can give an ordering of the roots. So it's a permutation of the roots, but it's an ordering. Now if I have two rooted graphs, each of them has an ordering for the roots. I can compare them in this way. If I say S plus with the ordering sigma S is less or equal to T plus with the ordering sigma T, that means T plus contains S plus as a rooted topological minor, and the ordering of the roots should be preserved. So if you see the branch vertex of S plus, the roots of S plus, it's a subsequence of the roots of T plus. Okay, so now I can define what do I mean a symmetric cover. So I have a cover C, and I call the maximal element of the cover by M1 through Mk. If this cover is symmetric, then the following complicated conditions should hold. So the condition is that for any permutations of the roots of the maximal elements, and for every plane drawing of edge, such that all vertex degrees fall incident with infinite phase, then the following complicated condition holds. So the first condition says that, okay, so now I can draw the graph edge into the plane such that all vertex degrees fall incident with infinite phase. And each member of the cover contains the vertex degree at least 4, so it must touch the infinite phase. So if I go along the infinite phase, then I can give an ordering of the graph edge. So say this is my graph edge, and some large degree vertex here. And each member of the cover contains some degree 4 vertex, like this. So if I go along the infinite phase, I can order the members of the covers. And because M1 through Mk are all the maximal elements in the cover, so for each member of the cover, I can find some Mi such that Mi contains this one as a rooted topological minor. So it means that for every member here, I can assign it to a maximal element. So now I assign each member of the cover to a maximal element. And by saying the cover is symmetric, it means that I can find such an assignment such that if I see two members are assigned to Mi, then every member in the ordering here should also be assigned to Mi. So that's the first condition. And we need more. So now I know I can assign each member to a maximal element Mi. So it means that I can find a rooted topological minor. So I mean, I can So Mi plus contains the rooted version of this member as a rooted torsion minor. So I can find the ordering of the roots such that the maximal element contains this in the stronger version, preserving the ordering of the roots. So for every member here, I can pick Mi and also pick an ordering of the roots of this member. If the cover is symmetric, then I must be able to pick such an ordering such that if you so I have ordering here like this. If I want to see the ordering of the roots in this way, is that if I go along the boundary cycle, want to see 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, then I need to permute these edges into 1, 2, 3, 1, 2, 3. After this permutation, I cannot create a cross in the middle. So that's what do I mean the cover is symmetric. So it's a very complete condition, but we need that. Okay, so now we can prove the theorem. These three necessary conditions, oh sorry, I didn't mention the third necessary condition. The third necessary condition is that every cover of the graph should be symmetric. So, and it turns out to be the characterization for connected graph. If a graph H is connected, then T of H has error disclosure property. If only if this graph should be able to join the plane such that O phase degree is 4 incident with infinite phase. And this graph has no cover containing 3 pairwise incomparable maximal elements. And every cover should be symmetric.
So 3 pairwise, so this is different from anti-chain, right?
No, I just say the maximal elements. You can have anti-chain of
But all maximal elements are anti-chain, right?
Yes.
So incompatible, you don't need to say incompatible.
I mean, I can have only one maximal element, but I have an anti-chain of very large size.
Yeah.
But the condition says I cannot have 3 maximal elements.
I see. So the set of maximal elements is at least 3? No, at most 2.
At most 2, yes. 1 or 2. Yeah. And actually, this theorem can be generalized to this connected graph, but it just makes the stuff much more complicated, and I don't want to mention it here. But you might ask, well, this characterization is too complicated. But by using this theorem, I can further prove that actually this characterization should be less complicated, because we can prove that if you give me a graph H, deciding whether T of H has error disclosure property, this problem is NP hard. So if I can have a very clean characterization, it means probably I can solve NP equals P easily. Okay, so it's unexpected to have an easy characterization. But this characterization is not bad, because it also gives us a pi2p algorithm to test whether T of H has an error disclosure property.
Pi2p?
So pi2p means
circuit of something? Or?
No, pi2p means if you have a no instance here, then you have a certificate that can be verified in NP time. To the iterated NP. I mean, NP means sigma 1, co-NP means pi 1, and pi 2 means co-sigma 1. Yeah. Okay. Yeah, okay, at least I have an algorithm. Okay, so let's try to prove this theorem. Okay, so let's make the case easier. So we assume the graph is connected. So I want to prove it by induction on K. I want to prove that for any graph G, either I can find K pairwise disjoint H torsion minors, or I can find NK phrases, a set of NK phrases that touch all H torsion minor. means that if I delete these vertices, then I have no topological minor at all. Okay, so now I assume the graph G has no k pairwise disjoint topological minors, and I want to prove I can really find such a set of vertices Z. And before doing that, let me define the notion called a separation. So a separation AB of a graph G is a pair of H disjoint subgraph, such that the union of them is a whole graph. So the separation just like this. The entire graph is G, and the left circle is A, the right circle is B. And there's no edge between these. There's no such edge. And the order of the separation is the number of vertices in between. So this one has order 5. So now suppose I'm very lucky in this case. If I know in A minus B, if in this side, I know I have one H topological minor. And if I also know in B minus A, in this side, I also have one H topological minors, then what do I know? Because in this side, I have one H topological minors. So in B, I cannot have K minus 1 H topological minors. Otherwise, I put this K minus 1 and at least one topological minor. I get K disjoint topological minors in G. So in this side, I don't have K minus 1 disjoint topological minors. So I can delete a set of vertices GB with size at the most n sub K minus 1. And similarly, and if I delete vertices, then B has no H topological minors. Similarly, because I have one H topological minors in B minus A, so in A, I cannot have K minus 1 disjoint topological minors. So again, I can delete a set of ZA with size also like this. So I delete two sets. Now I know A has no topological minors and B has no topological minors. But the remaining graph can still have topological minors. But if I have, it must touch both vertices in A and the vertex in B. And the H is connected, so it must touch the middle vertex. So if I further delete vertex in the middle, then I can kill all topological minors. So let's count how many vertices I delete. I delete ZA. It has size n sub K minus 1. Delete ZB. It has size at the most n sub K minus 1. And I delete the number of vertices in the middle of the separation. So that's the order of the separation. If the order of the separation is very small, then I can just define this number to be nk, and I'm done. So it means that if the easy induction argument doesn't work, then it means that there's no separation of small order have this property. Means that if I have a separation of small order, then exactly one side contains some topological minors. And so in this way, I can define the orientation of the separations, which tells us which side of the separation is important. So for example, if B minus A has a topological minor, means B is more important than A. So this gives us a tango structure. So this one is a formal definition of the tango. So formally, it's a set of separations, and they satisfy some property. But these properties just tells us which side of the separation is more important. So the first one just says, if you give me a separation AB, then either AB is in the tango or B is in the tango. And if AB is in the tango, means B is an important side. Okay, so the first condition just says, every separation of small order, I know which side is the important side. And the second condition just says, the small side, non-important side should be really non-important. The union of them cannot be the whole graph. And the third condition is similar. The non-important side cannot contain all vertices. So anyway, so it's just a tango. It's the orientation of the separations. It tells us which side is important. Okay, so I have a tango, and now my graph has no k disjoint h topological minors. But what's the graph look like? So we need a structure theorem, and here's a structure theorem. Actually, it's my earlier theorem. It's a joint work with Robin Thomas and I. So it's a very special case of that structure theorem. So assume H is a graph that can be drawn in the plane such that all vertices of degree at least 4. And if my graph, okay, so if I have such a graph H, then I have some constants such that any graph G with no this graph as a topological minor, then for every tangle of large order, I can delete bounding number of edges such that if for every remaining vertices, I can find a separation in the tangle such that this vertex is in the non-important side of the separation.
For every vertex V?
For every vertex not in Z. If I delete Z and I still have vertex in the remaining graph, then I can find a separation of small order that separate this vertex from the tangle. Okay, and it's exactly the case we want, right? I want to prove the 3 necessary conditions are sufficient. So now my graph H satisfies the topological condition. Is that exactly what it says at the top? It can be drawn in the plane such that all vertices of degree is 4 instead of infinite phase. So I know.
So this is like you have a small bag where the G set is. This G set contains something big in the tangle side and everything. And that set is...
It means...
and every vertex outside is on the small side with respect to tangle. But G is also small.
No, I mean the separation here are not cross-free. They can cross. I mean... So it's the graph G minus Z. You pick a vertex here. You find a separation separating this vertex and the rest of graph. And you have another vertex here. You also find a separation. But the separation could look like this. So you don't get tree decomposition in this case. But at least you know for every vertex you can find a separation with small order. Okay, so now I want to apply this to our case, right? So now my graph G has no k pairwise disjoint h topological minors. So it means G does not contain the disjoint union of k copies of H as a topological minor. And the disjoint union of k copies of H still can be drawn in the plane such that all vertices degree is 4 instead of infinite phase. So I can apply this theorem. So now I delete bounding number vertices. Then for every remaining vertex, I can find a separation. So if I delete this set Z, I still have H topological minor. Then I want to see what's the branch vertex. For each branch vertex, I can find a separation such that this one is in the non-important side. So for each branch vertex, I have a separation. If I take union of all such non-important sides, I get a separation such that all branch vertices are on the non-important side. And this separation still have small order. So the graph will be like this. So it's a separation, and I have many branch vertex, something like this. And so if you just see this side, you see a cover of H, because this one means the subgraph that is isomorphic to a H subdivision, and you cut in the middle, you know all the vertices are here. Okay. So it defines a cover, and then you use this, and then use another two conditions to prove the theorem. It's too complicated, I cannot explain it to here. Yeah. Okay. But the other conditions are important to finish the proof. Okay. Okay, so let's for topological minor. That's the dirty part. Now I want to change another graph containment relation. Let's call the immersion. This part will be cleaner. So immersion is a similar graph containment relation as a topological minor. For topological minor, so if I say G contains H as a topological minor, means that I can find the subgraph of G such that I can map the vertices of H to the vertices of G, and then map edges of H to internally disjoint paths in G. For immersion, it's similar, but now I don't want internal disjoint paths. I just want H disjoint paths, and that's the immersion. G contains H as an immersion if I can find such a mapping. So now I write the set of graphs containing H as an immersion by I of H. So now I consider the packing problem and the covering problem for I of H. But now the edges of H are simulated by H disjoint paths. So I should not find vertex disjoint H immersions. I should see H disjoint H immersions. So I want to pack them into the H disjoint copies. So for the covering problem, I should not use vertex to cover this H disjoint subgraphs, because if I have a vertex, they can incident with many H disjoint subgraphs. So I should use H to cover H disjoint subgraph. So it gives us another kind of H disclosure property. It's called the H variant of the H disclosure property. So formally just saying that any graph either contains KH disjoint such subgraphs, or you can delete bounded number edges to kill all such subgraphs. So one question you can ask is that, okay, so again, ask for the characterization for the graph H such that I of H has a H variant of H disclosure property. But the answer could be exactly difficult as the topological minor case, because you should see this counterexample. It's also a counterexample for saying this tree has no H variant of H disclosure property. Okay, so, but now I want a clean characterization. I want to see, so for finding a characterization for graph H means I want to find the conditions of H. But I know I probably have to put too much complicated condition for H. So how about if I put the condition for the graph G? It's a hosted graph. So can I make the characterization simpler if my graph G has some extra property? So let's go back to this bad example. So let's see what's happening in this graph G. You can see so many H cuts of size 3. So how about we increase the H connectivity, say 4H connected? Then what will we have? Actually, it's the correct answer to answer this question. Actually, in 4H connected graphs, you don't need any condition for graph H. So formally, for any graph H, for any number k, I can find a number n depending on k, such that every 4H connected graph G either contains k H disjoint H immersions, or I can find nk edges intersecting all such subgraphs. So this one is much cleaner than the previous case. But now I need to assume G is 4H connected, but just 4. And 4 is better possible because you see the previous example, we have so many 3H cuts. Okay, and the idea of the proof is quite similar. I mean, we want to do induction on K. And now instead of considering separations of graph, now I consider H-cuts. So now I partition the vertices into two sides. So there are edges in between, edges here, and some edges between A and B. So it gives us an H-cut. So the order of the H-cut is the number of edges between A and B. And the similar argument as earlier, we can prove that, well, for every H-cut of small order, exactly one side contains an H immersion. Otherwise, the easy inductive argument works. So again, I have an orientation of the H-cuts. So again, I have a tango structure. Let me call this H tango. And it's a formal definition of H tango. It's a set of H-cuts satisfying some tango axiom. Okay, but it's not very important. So again, now I need a structure theorem for graphs with no H immersions. So before to read these slides, let's consider, so if I give you a graph H, what kind of graph cannot contain the H immersion? Well, first, if the maximum degree of G is less than the maximum degree of H, then you cannot contain H immersion. But in fact, if the degree sequence of the graph G is less than the degree sequence of H, then you cannot contain H immersion because you don't have enough large degree vertex to dominate them. Okay, but the converse is not true. If a graph has degree sequence smaller than H, it doesn't mean G cannot immerse H. But in 4H connected graph, it's almost true in this sense. So it's a theorem for any graph H with this degree sequence. And I can find some constants such that if G is 4H connected, then I can find the set of edges with bounded size and the set of vertices whose size is less than the number of vertices of H. And the cross-free family of H-cuts, they have small order, such that if I see a vertex not in this special set of vertex, and I delete the bounded number of edges from the graph, then every remaining graph can be separate from the H tangle by a H-cut of order less than this number. So what does it mean? It means that, so I have a special set of vertices U. They could be wild. You can have degree very large. But if I delete bounded number edges, Z, then for every vertex, I can find the H-cut separating this vertex and the rest of graphs. Actually, these H-cuts can be chosen to be cross-free. So these sides are all disjoint. So if I contract each small side into one vertex, I get a new graph. And what's the degree of this vertex? It's the order of the H-cut here. The order of the H-cut is this much. So I mean, if you contract each small side into one vertex, you get a new graph. And the degree sequence of new graph is less than the degree sequence of U, because this one is less than this. You have U vertices have very large degree, and the next vertex has degree less than the U plus 1's largest degree in H.
But do you have this contract operation?
Yeah, if I contract the small side of the H-cut, I get a new graph.
But that's immersed.
I didn't say anything now. I just say if I contract the small side, I get a new graph. This new graph has degree sequence less than H. Right.
So you don't care about immersions yet?
Yeah, no immersion yet. But I mean, if G has this property, it must have no H immersion. Yeah. I mean, if G has no H immersion, then you can do this way. Otherwise, you have nothing to do. But you can see that this new graph cannot immerse H if I contract this small side of each H-cut. But if the original graph G immerse H, then this graph new graph will immerse another graph H prime, which is smaller than H. So let me put it this way. So now I pick a graph G that has no KH disjoint H immersions. Then I apply this structure theorem by taking not H, but another graph HK by just duplicate each H k times. If I have immersion of this graph, means I have KH disjoint immersion, H immersions. I cannot have this one. So I apply structure theorem. I contract a small set of separations, H cos. I get a new graph G prime. Because the original graph G cannot contains KH disjoint H immersions. So this, I can find the graph H prime that is smaller than H. That means the graph obtained by H by duplicating each H k times. I can find another H prime, graph H prime, less than this graph, such that this graph cannot immerse that graph. So now I apply structure theorem again. But I will have to stop with bounding number of times, because for each operation, I reduce the degree sequence of the graph I exclude. So in the end, I will get one vertex graph. The degree sequence should be all 0. And now I assume H is connected, so I can just have one vertex. And every graph should contain one vertex graph as an immersion. And it's H disjoint because no H at all. So it's a contradiction. So it means that if I delete bounding number, if I delete H is C for bounding number of times, I can kill all H immersions. Okay, and that's what this slide says, but it's not important. Okay, so thank you.